Alrighty, welcome back. So we've spent a good amount of time talking about hashing functions, SHA-256. Basically, outside the context of Bitcoin, we learned about SHA-256 on its own. We did some demos. We saw how to use it to store passwords safe-ish. And we also talked about using SHA-256 to verify the integrity of downloaded files and all sorts of things. We did all of that for a reason, because SHA-256 plays a super, super important role in Bitcoin. In particular, when we talk about blocks and the blockchain, which is what we're going to do now. So the next couple of videos are all focused on those two things, blocks and the blockchain. But first,
let's talk about databases.
Database.
So this is a database, and you might have encountered one of these before if you've ever used Microsoft Excel, or you've used Google Sheets,
or like a real database
like MySQL.
It's MySQL.
Yeah,
you can trust me. I'm not allowed to mention I have courses on things. I do not have a course on MySQL, and you should not look at it.
No, and if he did, it would have terrible ratings.
Okay, anyway, whatever database if you've ever worked with one, this is a silly example. It's trivial, but we're storing things in different columns. We have a date added, a name, and a favorite color. Some good colors. Yeah, turquoise, that's a great color too. No purple though, very suspicious. Purple should be on here.
Yeah.
Anyway, Bitcoin has a very important database called the ledger.
It's distributed ledger, and this is a simple ledger here. This extends our rainbow coin example, where we have Felix and Kilgore and Billy in Montana, and they are exchanging something. Let's pretend this is just rainbow coin. Now, Bitcoin's looks quite similar. However, the actual contents of the from in the two fields aren't names, they are addresses. Addresses?
Anyway, it looks like this. Instead of a person's name, to and from, and a quantity, we still have a quantity, but we have one address on the from and another address on the to. And you actually saw this when Kevin sent me 0.00 whatever Bitcoin that he sent. We showed the addresses, and we actually showed what it looked like in the block itself at the end of the day. So this is what's stored. It never says Kevin sent Colt. It says 1NSZ sent 1ZQN 0.5 Bitcoin.
Now, back to sort of our pictorial analogy, we use these envelope icons. Each one is a transaction.
Right. So each envelope is a from, a to, address, and a quantity.
Yeah.
And we're just simplifying it because our next slide shows that there's a ton of transactions together to make up the ledger.
Isn't it colorful?
Yeah. Yeah. All these colors just go great together, Kevin. Now, we really coordinated them.
So this is a tiny window on the sides of the ledger. The actual Bitcoin ledger is 300 million little envelopes. We couldn't fit that onto one slide.
So we put a ... there.
It's
the same thing. So this thing goes on really, really far, further than we could ever show on the screen. It would take hours to scroll through.
And all the way back to 2009. And this goes, if you remember our discussion of how do you keep an Excel spreadsheet secure, it's quite difficult. How do you prevent somebody from going in and changing one of those values? What would that look like here? Somebody could swap out this pink one for a teal one. Teal?
There we go. Yeah, so what that would actually mean, let's say that they're changing the quantity that was sent. Instead of 2 Bitcoin, it was 20 Bitcoin now that's being sent from one person to another. And remember, in Bitcoin, there is no physical object. All that matters is what the ledger says. And if the ledger says X person from X address to X address sent 20 Bitcoin, if everyone agrees on that, of course, then that's true. You have 20 Bitcoin in that address. So it's important to prevent people from changing things on the ledger, whether it's 10 years, well, not quite, actually, I guess almost 10 years ago, whether it was 8 years ago when the first transactions or yesterday. It doesn't matter, but you shouldn't allow anybody to change it. So I have an idea, Kevin, on how we can fix this whole thing.
To prevent someone from tampering with it?
Yes, we talked about fingerprinting. You could have a file like we did with our Ubuntu download. If anyone changed a single character, I fingerprint it and I can tell immediately. So we just spent a lot of time talking about fingerprinting. Why don't we fingerprint the ledger?
So if you remember how long it took to fingerprint our 200 megabyte operating system, Ubuntu, imagine needing to SHA-256 fingerprint something that is about 200 gigabytes, so something 1,000 times larger than that.
Right. And not only, we wouldn't just do it once, we would do it anytime transactions were added, right?
Yeah,
we need to keep doing it to make sure over time things in the past, nothing was changed.
Yeah, keep it up to date. So what does the Bitcoin network do? They break it into blocks, hence the blockchain.
Okay. Instead of trying to fingerprint all of those transactions all at once, 300 million plus, instead, We break them into chunks, and this is not an actual representation of the number of transactions in a block. We'll talk about how that's determined, but it is not, what is this, 15? It's not 15.
Yeah, it's in general up to 2,400 per block. It's about 1 megabyte per block.
Right. But remember, a transaction is just a couple pieces of information, so it's really easy to fingerprint a block. There isn't much space. It's just a couple. It's an address, another address, and a number, a quantity. So that's what we do. We take individual fingerprints of the blocks, and we have a painstaking animation.
This is good.
So transactions come in.
Accumulate, more and more and more. And then when we fill a block, we save a fingerprint.
Right.
Then more transactions come in.
Oh, there we go.
And then when we fill a block, actually every about 10 minutes, new fingerprint. We save a checkpoint. And we keep going. More transactions. And then we get a full block, or we reach 10 minutes, and voila, another fingerprint. And this is what, we have a history of these fingerprints. And if somebody wants to go back and modify an old block, then they would have to fix one of these fingerprints. We're going to talk about the process in which these fingerprints sort of accumulate on top of one another.
Right. So we're really just focusing on the concept of individual blocks right now. There's also the blockchain, which we're kind of showing you here by chaining multiple blocks together, but we have a whole other video on that. So for now, the key concept is instead of one massive ledger, we break up the ledger into chunks roughly every 10 minutes of transactions, 2,400 transactions roughly, into a block. And then we fingerprint those individually rather than trying to fingerprint 300 million transactions together. I don't know why I have this analogy in my head. Like at a sausage factory, you have this long pipe, this super long tube.
That's a good analogy.
Like I guess intestines is what it used to be. Now I think it's often cellulose.
Just plastic.
And you're filling it with meat. Those are the transactions. But you don't just make one massive sausage. You twist it off into smaller sausages.
That's a fantastic analogy.
Every X number of or I don't know how many inches or whatever it is. There's some metric that makes it divided into a chain of sausage links.
So every 10 minutes, the miners tie off a sausage.
Yeah.
That's great.
So imagine that we have these two blocks, or one block, and the original, what it's supposed to be, is on the left. But some bad actor changes one of the transactions.
Bad guy, Hans Gruber.
Yeah. So there's something bad. I don't know. Deleted a transaction or falsified information, changed a character, whatever it is. Well, we wouldn't spot that probably as humans. Looking at the numbers, like we're not going to go through and compare line by line each transaction. But when we fingerprint those blocks, suddenly we can see the discrepancy, because remember that one of the key things of these hashing functions, a small change in the input has a large effect on the output. You change one number, you add a zero, instead of 10 Bitcoin, it's 100 Bitcoin in that transaction. That's going to radically alter the output of SHA-256. So when you fingerprint this block, even though it's only one tiny transaction out of 2,400 or so, and it's only a single zero that's changed, it still has a huge
completely
change.
Different. Yeah. And it is miners' responsibility to make sure that these fingerprints are correct. And instead of actual fingerprints, it is these guys, SHA-256 hashes.
Right. So SHA-256 already, there's actually more we haven't talked about. When we talk about the blockchain, we'll get there. But you can see that SHA-256 plays a really big role in keeping Bitcoin secure. All right, we finally made it to one of the buzzwords, the trendiest keywords of the year.
It's hip,
the blockchain. So we've been building up to this for a little bit. We basically had to start by covering the basics of a currency, talk about the existence of a ledger, talk about addresses. Then we had to talk about fingerprinting, talk about fingerprinting individual pieces of the ledger, which are blocks. Now we take it one step further. We talk about the blockchain. So where should we start, Kevin?
What is a blockchain?
So blockchain, according to whatever definition we sourced here, a community-maintained database of transactions which grows but cannot be modified. So the keywords here are community-maintained, meaning that it's distributed, many copies of it, and then also it cannot be modified. So let's compare that to a traditional database, which is, you could have a database of transactions which grows. That's not unique. What makes something a blockchain?
So on the left, we have database. So this would be the traditional way of organizing, say, Rainbow Coin. And then on the right, we have blockchain. So a database is modifiable. You can change whatever you want in it, and there's no indication that something has changed.
I think of just a spreadsheet when we say database, or Kevin says database.
A database.
Anyways, whatever we call it, think of on the left, a spreadsheet, Google, Excel or Google Doc, and on the right, blockchain, which is, we're going to get into some diagrams of that in just a moment.
Now, the database on the left is also typically centrally maintained, so it's maintained on one computer. Maybe there's a couple of backups, but the blockchain, the innovation there is that it's maintained on many computers. There are tens of thousands of copies of it, as opposed to the database where it's really up to the database maintainer to keep a couple of copies, and there's no enforced comparison between those copies and the master copy.
Right. Okay. So other than that, though, I mean, a blockchain is basically just a growing list of transactions. You could do that in spreadsheet. The two things that we already mentioned, that it's not modifiable in the past, at least we're constantly adding to it, so it is being modified in that way, but you can't update or delete previous values or change things that have already been cemented in the past.
So you're going to see this slide a few more times in this course, but we show this to divide the two uses of cryptography in Bitcoin. So what we've been focusing on, fingerprints, hash functions, is really the first half of Bitcoin's use of cryptography, proving the integrity of its ledger, making sure that nobody tampers with it. And that involves fingerprinting it over time, and that's what's called the blockchain. This is just one-way hash functions.
So in the last video, we talked about how Bitcoin takes advantage of SHA-256. It splits up the massive ledger into smaller sub-pieces called blocks, and it fingerprints each individual block. And that's great. That adds some security, and it's also easier to fingerprint individual blocks rather than the entire ledger. But it's important to note that it's not continuously rehashing every single block in history, right? So something's hashed 5 years ago, let's say, and the block is done. Somebody between then and now could go back and change it. And if Bitcoin works the way that we've described it to you so far, we would have to continuously rehash that block from 5 years ago and just check. Is it the same? Is it the same?
Is it the same? Yeah.
And that's difficult and time intensive and computer intensive.
So instead, one of the huge innovations in Bitcoin is the notion of chaining the blocks into one another. So right here in our diagram, we've replaced the top left transaction with, instead of a transaction, which is just a little piece of data, with the fingerprint of the previous block. And we're going to spend the next several videos talking about why this is so useful, why this reinforces the security of the blockchain so much.
Yeah. So we've kind of been, I won't say lying, but we've been omitting the fact. We've just been saying that a block is a bunch of transactions. And we're not showing the full picture to you yet.
But we'll get there.
One really important piece is that it contains a hash, a fingerprint of the previous block. So rather than the actual fingerprint, it looks something like this. So we have all the transactions plus the hash of the previous block. And then we would hash this block when it's done, which includes the hash of the previous block. So then the next block has a reference to this block, and it keeps going on and on and on.
So as we fingerprint each block, we're including in the data that we're fingerprinting the actual fingerprint of the previous block. And this is going to be hard to digest right here. It'll be easier once you see in examples when we show the full diagram. But really, what we're trying to drive here is that in each block, you can include information about the previous block. And that's going to really reinforce the history, the historic security of the blockchain.
Yeah, because if every single fingerprint you take of a block is based off of every block that came before it, if somebody changed something 5 years ago, then all that difference is that change is going to cascade all the way down to modern day to today,
to now. And get these hashes off the screen.
Okay.
We need emoji.
So here's a couple of
much
examples.
Better.
What we're going to show is that if you just, what we've been doing before, we're replacing the actual hash, the results of SHA-256 with emoji just to show and visualize. If we have the exact same transaction, so the envelopes stay the same color, but the previous block, the emoji representation of it changes, it leads to a very different fingerprint of this entire block when we include this piece in there. So then let's say somebody alters something in the past, and just the last block. Well, now the hash of that last block is different. It's now a purple umbrella, which I wish I had a purple umbrella. And then we take the fingerprint of this entire block. The transactions are the same. No colors have changed, just the previous block's hash changed. So now the fingerprint is totally different. Just like changing adding a period to the entire text of Moby Dick, massive difference. In this case, going from a peach to an ice skate. Wait, we have a couple more. All right, I'll fast forward through these. But anyway, you can see, you change the emoji, you change the fingerprint, you change the entire block's fingerprint.
So what's it look like when we chain them together? we actually have a reference to the previous block in every single block. So that means if somebody wants to go in and tamper with maybe even just the last block, that's going to change the fingerprint of the current block. So here's the emoji version.
There we
Much
go.
better.
Okay, so you can see that this first one has a rainbow emoji as the previous block. So we hash that with its transactions and we get the peach emoji. So then we take the peach emoji.
Looks like a butt.
Yeah, Kevin, this is a PG rated course.
The butt.
I'm offended. I'm really offended. Okay, so we have a peach. We put that in the next block as a reference, and we say, okay, if everything goes to plan, nothing has been changed, the previous block's hash is a peach. Then we hash that with the next block, and we get a purple umbrella, and then we would put that into the next block in the future and say, hey, the last thing was a purple umbrella.
So zooming out, pretend that we have 3 blocks in all of our history. We've crunched it down. We just have a little tiny network, but we want to make sure that nobody can tamper with any of the old transactions. Mm-hmm. The first hash was a rainbow, and you'll see in the top right of that block was what color was that?
That's blue.
That's a different color than blue. It's like a cobalt.
Okay, that's blue. In general, it's a blue.
I think it's a warm cobalt.
It's a blue envelope, and somebody tampers with it, and they change some value in there. They delete a transaction.
They change it to an orange.
There we go.
Now, the fingerprint of that entire block becomes a taco.
Yep.
Which is just, remember, these are just representations of the underlying SHA-256.
Yeah, now it's 37077 instead of 2BA7.
1.
Yeah. Anyway, so we're using emoji.
Yeah, so what happens to the next block? If you want to have a valid blockchain, you need the previous block, this little rainbow in the top left of the middle one, to reference the first one. So you would update that guy. But then when you update that guy, the butt emoji would become a hand emoji, which is the punch somebody hand emoji.
Punch somebody? Isn't that okay?
When you go like this, doesn't it mean I'm going to punch?
Ow!
Then, I think that's the A-OK emoji, or the punch somebody emoji, would propagate out to this block. We update this guy, and now the umbrella that most miners are looking at right now doesn't make sense. Because the hash of the current block doesn't give us an umbrella. And that...
It gives us a pufferfish.
Pufferfish.
Which is
I like that pufferfish.
I do like pufferfish. So what we're trying to say is that if you're a hacker, you're trying to change something in the past, and let's say we have more than 3 blocks, let's say we have thousands of blocks, and you're trying to change some transaction in the past, you're going to have to update every single block, and not only that, you're going to have to convince everybody else that they're all wrong, and that instead of a purple umbrella, they should actually be getting a pufferfish, which is really difficult to do because the key takeaway of this is that as time moves on and there are more and more blocks, it's harder and harder to change things in the past. Things get cemented under further layers of security. So we are not done with the blockchain. That's not our only explanation of it. We have a visualization we'll get to, but first we have to talk a little bit more about what else is in a block. And then we're going to actually show you a lot of an interactive demo, and we're actually going to look at the blockchain and see how you can take the hash from the previous block and actually look at it in a current block. So we'll get there. Hey, welcome back. So what we're going to do now, I think it's kind of cool. We're actually going to show you the blockchain, or at least a visualizer for it. This isn't the actual blockchain itself. This is just using the data from the blockchain, a company called Blockchain. It's very confusing.
This is the wallet we used earlier on.
Yeah, it's a private company called Blockchain. Very confusing. But they create this visualizer for us that we can go and explore and look at transactions. But it's not an official thing. It's not part of Bitcoin. It's just using the data that any miner has access to, just putting it online and making it clickable. So what we're going to do here is, well, first I just wanted to show you, these are all the blocks mined today. And you could go back in time. You could keep clicking previous forever and go all the way back to 2009. You can also search for a block up here, or using a particular transaction, you could search up here.
But now what we're going to do is look at the most recent block. So if you look up top, it's listed by height.
What's height?
Why is it called height? So in our diagrams, we've been growing a blockchain horizontally. And that's just because the slides fit better that way.
Yes.
The blockchain is described as having a height because as new blocks are added, as new transactions are added, they're stacked at the bottom of the list, or the top of the list. I think it's easier to think of it growing downwards.
So we're basically at block number 520,093.
Yeah, so since 2009, there have been 520,000 blocks, and people are working on the 520,094th block right now. But 13 minutes ago, 520,093 was mined.
Okay.
So let's look at it.
Okay, so here we are looking at block number 520,093, or is it 94? We started at 0, right?
Depends. There is a bug in the code. Yeah, so we can call this, I think right now they're based on 0, so that this is the 520,094th block.
Okay. So if we skip the headers for just a moment, you can see these are all the transactions. I think, look at my scroll bar over here. There's a lot of transactions here. It's going to take a while to scroll through them, and I'm going to give up. But roughly, we can see that there is a from address and a to address, or addresses.
Yeah, there's two addresses.
And before we talk about that, there's also the amount.
Yeah.
So why are there 2 addresses?
So when you create a new transaction, you actually don't keep any of the Bitcoin in the Dropbox that you open. You effectively throw out that Dropbox and create a new one for yourself. Remember that you can create as many as you want. So the secure way to move Bitcoin when you open a Dropbox is to actually split it up. You send what you want to send to your destination, and then you send the change, you send the leftover, to somewhere, to a new address that you own. We'll describe that in greater detail later.
So let's just say this is you. It's not. Let's say this is you, and then this is me.
Yeah,
and
so
you're
sending 3.39.
Yeah.
Yeah.
And then you have some left over in that first address. It gets sent to this.
Yeah.
Okay, so that's actually not what we're trying to talk about here. That's just something we felt we should mention because it is confusing that there's 2 addresses. But let's go back to the top. What we want to focus on are these little lines right here. So you can see there's number of transactions. There's what else do we have in here? The timestamp and the size of the block and a couple other things. But what we're going to focus on are the rightmost pieces of data here, the hash and the previous block. So let's start with the hash.
So the hash is the hash of the transactions in the current block.
Right.
It's a bit of a simplification. The hash is actually the hash of the header. And we'll describe what that bottom hash, the Merkle root, is. But you can think of the top hash as the hash of the current block.
Okay.
And the previous block down below it is a reference to the block before it, the hash of all of the information in the previous block.
And before we click on it, let's just look at the last little bit.
Sure.
159CF. All right. And I could click on this it would take me there. But to be clearer, we're going to go and just make sure we're clicking the previous block here, 520,092. Now let's look at the hash of it. There we go.
59CF.
59CF. And we could do that one more time. This time, let's look at the hash of the previous block is supposed to be A04D. And we're at 520,091. And we look at the hash, A04D. So...
And this continues all the way down. Turtles all the way down to the beginning of time.
Yes. And if we were to change something, then that would alter the hash, right? We saw that in Moby Dick, we capitalized one letter, an L, it changed the hash entirely. So if we were to change a number, an address, a transaction amount, any of that, or insert a transaction, for example, or delete one, that's going to change the hash, which means that in the next block, the reference to the previous block is going to be wrong.
All right, so to demonstrate that, we have a simplified blockchain right here, and we've inserted some fake data in these data fields.
Very simplified.
We've got one transaction per block. Each one of these rectangles is a block.
Okay.
And each one of them has data.
Instead of, what was the last one we looked at, 2,600?
Yeah, these each have one.
Okay.
And we're just bringing up this page to show you what happens. See how if you look down here, we have the previous hash of each block that references the previous and the current hash.
Right.
And if we go to the left, we go to the beginning of time. Left is oldest. If we were to change the Kevin to Colt, if Colt was to feel like a jerk and somehow want to change this to a 10 Bitcoin transaction, what would it do to the rest of the blockchain?
Well, all of the future blocks, there's only 4 other ones, but those 4 blocks ahead of it are referencing this previous block. And then this one is referencing this previous block. And so if something goes wrong here, you'll just see what happens. It's going to cascade across, and it's not good. Oh,
Danger.
No.
Red.
So now everything's red.
Yeah. So the chain of hashes is now invalid, is now changed.
Yes.
And that's a good indication to anybody looking at the front of the blockchain with, say, a wallet or a cell phone or a simple mining rig that something has gone awry.
Okay, so we fixed it. So we're back one more time. We have the correct data again. But I'm just going to show that if we pick one, let's say in the middle, and I change this Colt to Kilgore is now going to be 21 instead of 2.1.
Why would you do that to yourself?
Not 2/1.
21.
I had one job. Delete that period. I couldn't do it. So you can see that the previous transactions are not at all red, and red in this case represents just
something's wrong.
Yeah, something is messed up. But going forward, everything from that point forward is wrong because they reference the previous block, and then this is hashed, and this references that hash, and so on. And remember that you changed one tiny thing, so the reference to the previous block changed, the entire hash changes because it's hashed in there together.
And if you're having trouble with this, if you're having trouble following these little hashes, don't be too worried. We're going to really dive deeper into this, and we have way better emoji-based diagrams on this in the coming chapters.
And then we'll also learn what the heck this mine button is actually doing.
We will revisit this.
Yes, this is just a quick visualization.